You see, instead of using level set, we're talking about using the characteristic functions. And then we relax these constraint characteristic functions. We show that for this special model, the relaxed, and this is a complete convex problem equal to the original non-convex problem. So this is very simple. This is very simple, but you can see that this idea you can use this similar idea in other situations. Even we are going to talk about one a little bit later. So the second thing we talked about was really using graph card for image segmentation. So this is a graph you construct. You just assign those constant. You assign this capacity. So here is essentially the image intensity distance to C1 square. Here is the image distance to C2 square. Assume C1, C2 are known. If you don't allow any flow here, and then the flow must goes up here all the way from here up to there, and then you can see which one is the smaller, and that edge will be cut. You see, that's essentially threshold. You see which constant belong to that class. So this is a simple threshold. But however, if you allow flow in between the neighbors, and this will not be threshold, So if you don't know the constants, so you first guess a constant, and then to get the regions. If you don't regularize, essentially you just do the threshold and then average the constant go back. And we see that this is a k-mean and this is a multi-phase case. For multi-phase case, especially k mostly means how many cluster you choose. So we can see exactly from here. Here we only do for two constants. If you do more constant, we see exactly. You see that k-mean is trying to minimize this one. You're just alternating between those two. So given Ci, found omega I is usually you found which constant is the nearest, and then once you get the omega I, you do the averaging. But one thing we didn't talk is that in fact what's k-mean? So k-mean, in fact, this you see this one exactly equal to this one. If a Ci, omega I are given, so this equal to this one. Did you see it? So essentially here I wrote in the whole omega I, but here is the input image. Here or minus Ci in omega I, but here is the I from 1 to chi Ci. Here is a characteristic in omega I. So this is exactly equal to this one. If a Ci omega, for any given Ci and omega I, this functional equal to this functional. And so therefore what does it mean? So this is a given function. And this function, so this function for arbitrary Ci and omega I, this is an arbitrary piecewise constant with k pieces. So this means the k-mean is essentially you try to find the piecewise constant approximation, find the best piecewise constant approximation with a k which is a given number, k is a given number. So this gives a very easy variational interpretation for the k-mean. So the k-mean is nothing else. You try to find the piecewise constant, the best piecewise constant approximation. So you don't know what's a constant value, you don't know what's the region the function is constant. So you minimize both Ci and omega I. So this is trying to do the best with piecewise constant approximation. That's a variational explanation for the k-mean methods. So if we put a regularization term here, and that's essentially the transverse or piecewise constant Mumford-Shah. So we can say that piecewise constant Mumford-Shah or the transverse is a regularized k-mean. And now we are trying to explore the relationship between graph card and transverse model. So for graph card, so this is a graph we try to do for one dimensional signal. We try to separate into two classes. So here is a cost here, here is a cost here, here is a cost. So now we allow we put a half alpha because there are two edges. If you cut two and then you become 1 alpha. Again, related to the question what he asked about this alpha, we just take a constant now, but you can also put it as an edge detector. There is no problem. You can also put the edge detector. So here we just put the constant. So, and then you see what, and then for such a given cut, if omega 1 is where the pixel equal to 1, omega 2 is where the pixel of 2. So therefore the cost of this cut, so the cost of this cut is essentially sum of those capacities. So you just sum the capacity in omega 1 and sum the capacity in omega 2. So those are the cost. But then also you see once you have a jump here, and then you cut two of them. So and then here you have alpha, here is a jump, because the jump is always 1. So this is the cost of those cutting edges. So this is the cost of the capacity of these edges. And so therefore this is the cost of a cut. So this is the cost of a cut. If you want to minimize the cost of the cut, so essentially every cut can be marked by 1 or 2. So if you want to minimize the cost of a cut, essentially you are minimizing this one if you do the graph cut minimization. Do we agree? So therefore you found the minimum cut is essentially you are trying to solve this minimization problem if you write it another way. So this is a minimum cut. So for everything here I use 1 to very often I use 0, 1. So this is you try to find the cost of the cut is given by this. Here is the arbitrary cut. So you try to find one cut which is the smallest cut. So this is the mean cut. Another thing. Here P you see here sum of NAP and Q is the neighbors. So in the 1D case, QP is if P is here, QP is just those two neighbors. P given here. So here you sum the neighbors. Essentially, a minimum cut is trying to solve this minimization problem for this graph. There's one thing I try to point out. You see, here is the minimum cut problem. If we try to think that this is a discretization of a continuous problem, and this will be the corresponding continuous problem, right? If you just think this is a finite difference or it's a discretization, and this will be the corresponding problem. This will be the corresponding problem. Now you can see that this is in fact nearly nothing else but the two-phase transverse. So here is the total variation. Here is the omega 1 I minus C1 omega 2 I minus C2. So this is if you write in this way, you can see that it's nothing else but the transverse model we have been talking, or the two-phase piecewise constant Montfort model, right? So exactly. So in this way, you see the graph cut is just another way to solve this problem. Mostly, you see, we replace by characteristic because I use 1, 2. If you use a 0, 1, so here is a characteristic function, and this is so this shows the connection between the graph cut and the piecewise Montfort or the transverse model, right? So it's just another way to solve this problem. So graph cut is a combinatorial way to solve this problem. Once you write in this way, you see very, very clearly. So even if it's a graph cut, you're solving such a problem. Also, you see in the discretized setting, so now I'm using 0, 1 instead of 1, 2. So very often I switch between 0, 1. Because in the earlier day we use 0, 1, but later we found that for binary case, mostly people use 1, 2. So it doesn't matter. It's just shifting. So in the discretized setting, so here is the cost of the F1 edges, here is the F2 edge, here is the jump. In the discretized setting, if you put the 2 here, it doesn't matter, right? Because the jump is 1. You see, 1 to the power of 1 is 1, 1 to the power of 2 is still 1. So if you put the power of 2 here, it doesn't matter. If you put the 2, this function looks more convex. You increase the convexity. Even become a linear. So therefore, in the discretized setting, this looks very natural, appealing. But however, you see, if you do this one in the continuous setting, this will not be allowed. because this function is a 0 to 1, so du square, it doesn't exist. It doesn't exist. And so therefore this also shows, you see, why we should study continuous functionals instead of only discretized. Discretized very often is such a kind of quantity, many other quantities, if you do it in the discretized setting, and sometimes you see there are some intrinsic natures, you do not understand it. But once you write in the continuous setting, and then you see more of the intrinsic settings. Because this function has a jump, so therefore du squared, this doesn't exist. So you can only, yeah, this is the, you can only, here you can only use the TV. TV exists for this continuous function. So this is, I'm just trying to use this example to show, I think for this kind of, there's two groups. One group just work on the discretized. Another group always work on the continuous. For the continuous, you see, we are mostly like a PDE people and continuous minimization people. And there's another group where they always work discretized. So there sometimes in the discretized setting, you may not see the essential things. And this is one point I want to emphasize. That was 1D. So therefore, if you want to use the idea in 2D, so this is a graph you should construct. So you have a 3 by 3, the image is 3 by 3, and there's a natural connection between the pixels, and you add the source here, you add the sink here, and still here the upper part, assuming C1, C2 is known, the upper part is the image intensity minus C1 square. Here the lower part is the intensity minus C2 square. Here you have a two-direction connection. You assign one constant, but you can also assign edge detector. If you do this one, so a natural cut, assume you see like this line is a cut, so which means all those thinner edges are cutted. The down is all those thinner edges cutted. So the cut is like a surface. So you cut through here and then goes up, cut all these edge, cut all the other edge. So this naturally split all the pixels into two classes. And again, we can show that if you found the max flow or mean cut for such a network, I think I didn't write it down. I never write it down. This is, yeah. So this is, this is discretized. So here I'm just using another way to, so here is my pixel, is my two-dimensional image. You have 5 pixels, you have 5 pixels, you add the source, add the thing here, everyone connect to source. So here the capacity here is intensity minus C1 square. The capacity for each pixel here is intensity minus C2. If you do a cut, assuming this is a cut, so that means you cut the edge on this side cut. And these give you, so the cost of this cut, if here is F1, so here is Fp, assuming if phi equal to 1 in the red region, phi equal to p, any cut will give you a unique 0, 1 assignment for phi. If phi equal to 0 here, phi equal to 1 here, here will be omega 1 capacity, here omega 2 capacity, and the cost here, you see that what's the cost here? We use this is we use, you see, phi p minus phi q. Phi p is here, phi q is the neighbors. So phi p is minus phi q. So this is trying to approximate the TV, So therefore, if you do such a cut in 2D, so this is the cost of the cut. This is the cost of the cut. And so you are essentially minimizing this problem. If also, I think I didn't write it down in the continuous case. The continuous version for this one, I think is like you minimize phi 0, 1. So this is a cut. And so here the first part here, alpha WPQ. So the first part, in fact, you get ux plus uy. The second part is like a phi. So F1 is C1 minus U0 square plus 1 minus phi C2 minus U0 square. So this is, you see, for people who are familiarized with the discretized, they always prefer to look at that model. But for people who want to use a continuous setting, so this is essentially a discretized version for such a minimization problem. And so therefore here you are minimizing this TV. Here you are minimizing this TV. If you and this TV does not approximate length. If you really want to minimize this TV, especially if WP1 equal to 1 and this Q, you see Q is in the neighborhood, if we just count for any Q, if we just count 1, 2, 3, 4, if PQ equal to 1, if this just contains the 4 neighborhood, and this is corresponding to minimize such a continuous problem. It's a discretized version for such a minimization problem. And here the TV is a UX, UY. So this is not a rotational invariant. If you really want to minimize this TV, so this will give you the length of the discontinuity, and then you need to use a more neighborhood. So here you need to use more neighborhood. So this one, so if you only use a 4 neighborhood, then you can increase the number of neighborhood. And there is a formula from geometry. So when the neighborhood is getting bigger and bigger, and then you need to properly choose the weight between those neighbors. If you choose this one, you can again approximate the length again. So this is the so-called Boykov and Kolmogorov. They use the Corsi Crofton formula. So instead of using 4 neighbors, you can use 8 neighbors or 16 neighbors. The more neighbor you use, and then you choose this WPQ properly, the more neighbor you use, and the better approximation you approximate this length. So therefore, this is another using GraphCAD for 2D. So how do you use it? Essentially, you see our student, what they do, they just download the combinatorial minimization. There is a fixed amount of, they are available algorithm. Mostly we just download some ready algorithm from even from the web page of Kolmogorov, Boykov and Kolmogorov. So mostly we have tried with push relabel and augmented pass. So those are well-tested algorithms for combinatorial minimization for GraphCAD. We just download their algorithm. We don't do anything, and we just use one subroutine to specify all the vertices, and then another subroutine to specify all the edges. So which vertex is connected with which vertex, and how much is the capacity there. And that subroutine is needed by their algorithm. We just run their algorithm, get the cut, and we plot the segmentation. So we don't do anything with the algorithm. So we just supply those capacity and use their algorithm. And once you get the TS sink source separation, we just plot it the corresponding. We do this one for 2D and 3D. So this is how to use a GraphCAD for image segmentation. So there you can see that as one of the questions yesterday who asked, you can see the GraphCAD normally it's very fast. It auto performs the continuous minimization, most of the continuous minimization in practice. The weak point is that you must memorize the whole graph. You must memorize the whole capacity. So this is very memory consuming. Mostly you can use this one for 2D images. Once you come to 3D, it doesn't work. And also you see like a push relabel or augment pass, they are not gradient-based methods. It's a combinatorial. So you see like the augment pass, you find any pass, you push the maximum amount of flow along that pass, and then you find another pass, and when all the passes are saturated, and you come to the global minimizer. So it's like it's not gradient descent, you slowly minimize the energy. Instead, you found all the possibilities. When there's no other possibility, you reach the minimum flow. So that's another thing. It's very difficult because that's not the iterative methods. It's very difficult to run that algorithm on GPU. Mostly you can run it on CPU. So that's another weak point, because for image processing, mostly we want to use the GPU. GPU is parallelizable very fast. That's another weak point. What's the other weak point? Right, I think maybe those two are the essential two weak points. Yeah. Once you observe this relationship, and now we are trying to turn everything into the continuous case. So graph cut, because it's combinatorial, so you always guarantee global minimizer. Graph cut algorithm always, when you finish the calculation, because only finite possibilities. When you finish the computation, the minimizer you get is always a global minimizer. So that's a good point. You see, all the methods we are talking so far, very few of them can guarantee global minimizer, but graph cut always guarantees. And now we are trying to see, can we really carry all those things into the continuous setting, and that's the continuous Max flow is trying to do. So here is a thing we just did using graph cut. You add ft, so here you f1, f2, and here is the neighbors. I use a uv to indicate the vertices instead of p, because p will use. So this is the same as the previous slides, but just changing the notation, because we will use p as a flow. And so this is the minimum cut formulation for such a discretized graph. So this is the minimum cut in a mathematical way. You can write in such a way. So a cut is essentially minimize such a thing. This is region 1, this is region 2, this is the regularization, and this is a cut. So this is the minimum cut in the discretized setting. We know that in the discretized setting, a minimum cut equal to the max flow. And so therefore, for such a network, what's max flow? So the flow from here to each pixel, and then flow to here. So the maximum amount of a flow, and there is a flow conservation. There is no flow disappeared during inside the network. There is a flow conservation. So the max flow is equivalent. If you sum all the flow here, or you sum all the flow here, they are equal. So that's the amount of a flow. So here is a flow. So you sum all the flows except essentially you sum all the flows here. And so here is a capacity constraint. So for the flow here, we assume is bigger than 0, less than f1. For the flow here, we assume is bigger than 0, less than 2. So the flow ps is from source to, and pt is from here to t. Here is a capacity between the edges. So here I think you can also require I think we don't require bigger than 0. In the negative direction, it's negative. I think here also bigger than 0. So here is a flow between the pixels. And so those are the three flow constraints. And here is the conservation of the flow. So the total amount of a flow in the system is conserved. So here is a flow into one pixel. Here is the sum of the flow in and out from that pixel. Here is minus spt. So here the total amount of a flow is conserved. And so here is, so therefore this is the mean cut, a mathematical formulation for the mean cut, and this is a mathematical formulation for the max flow. And those two are equal. If you solve one problem, you solve the other problem. Mean cut equal to max flow. So this is another way. And so therefore we have seen that what's the continuous formulation for this one, and then we can also get a continuous formulation for this one. Right? We can have also the continuous max flow. So which is essentially this is a discretized version for another continuous formulation, and this is a continuous formulation. So here is a discretized. We try to make it continuous. So the max flow in a region instead of max flow over a network. So in a continuous setting, you see here you add 1 point. Every point has a connection to S. Every point connection to T. There is a flow to every point. And so here is a total amount of a flow into the system. Here is in a continuous setting, you can write, so here Gx is essentially edge detector or constant. But the conservation of the flow totally in the system will become a divergence Q minus PS. This is the total conservation. This is a continuous case. You see, for people working with PDE, so normally feel more comfortable with such a formulation rather than the previous one. So the previous one, so this is essentially, so this is we can see that this is a discretization of this is the continuous max flow. Continuous max flow. And then once you do this one, I think Gilbert Strong was the first one in '83. He has already noticed this idea. But from '83 after that, there is not much. So people didn't pay attention to this idea. We didn't know anything, any people other than Gilbert Strong, who has a paper about this idea. So once you do this one, and then we discover something which is very interesting. Assuming we try to solve this max flow, we try to solve this max flow problem, and then there is an equality constraint. We try to use Lagrange multiplier to enforce this equality. Here lambda is Lagrangian, so you max the flow. You minimize the Lagrangian. Here is a constraints on the capacity. For this one, if you eliminate, you can eliminate PS, PT, and Q. If you eliminate all those ones, it turns out this is the if you eliminate all the flow variables and turn into a minimization for lambda, this is the corresponding minimization for lambda. I guess if you look at this one, all of you feel very familiar, right? So this is essentially the min cut. This is essentially the min cut. And also, you can see that the lambda, in fact, which is a Lagrange multiplier, turns out to be the cut. So the cut you want to find, in fact, is just lambda is a Lagrange multiplier, and for the flow conservation. This is quite surprising. This is quite surprising. This is quite surprising. Yeah.
In the discrete setting, you have inequality. PS is larger than 0, but in the continuous setting, you don't have.
I think we need them to be larger than 0. Yeah, we need them to be larger than 0. Mm-hmm. So therefore, this is quite surprising. Quite surprising. And the Lagrange multiplier for the flow conservation turned out to be the cut. And the flow minimization, maximization. Even there's another thing which is Chang, Acidoglu, Nikolova. They didn't use anything. They just use another thing, and they have also came to this model, but not through the max flow min cut thing. So they did these ones from another. Here, moreover, you see here the lambda is a 0,1. Lambda is a 0,1. And this is something very interesting in the continuous case. So in the discretized case, you don't observe. In the continuous case, you observe. And then this problem, you see, this problem is convex. This problem is non-convex. But however, the real deal problem in the continuous maximum case should be this one. We can prove. You see here, this will be convex. And then you need to prove that once you threshold it to 0,1, it's still a minimizer. It's still one of the cut. It's still the one of the cut. And this is something very interesting, and this is new. This is quite new. This is quite new. Especially I think for people working with minimization, a lot of people may be very familiar with these kind of problems. You may explore a lot of possibilities, So here I'm trying to emphasize what's the meaning of this approach. Is the combinatorial problem is minimizing energy function, not using the descent info in the energy. So graph cut, you don't use even you minimize the energy, but you don't use the descent methods. Essentially, they just exhaust all the possibility, and then you found. But when you exhaust all the possibility, you eliminate many things very, very easily. You don't need to do all of them. Is the argument possible push of label? So you don't use a gradient descent. The continuous mark for mean cut is a convex minimization problem. A lot of choices can use descent. So we turn it into a convex minimization problem. And then there's no need to use a push relabel augment pass. You can use many other things. You can use a gradient descent, you can use a Newton, you can use a fixed point, anything you can use. You have a lot of possibility. So continuous mark flow may not be a cut during iteration, will be a cut a convergence by truncation. So here one thing is here is for the continuous mark flow, the deal problem is a convex. If you want to get a binary, you need a threshold here. That's something you need to prove. But I should say that not all combinatorial problems can be convexified. So this is one way to convexify. This is another way to convexify this non-convex problem. So this is a non-convex problem. In fact, if you consider the max flow, it will be naturally convex. Guaranteed global minimizer, even you see the function is a nonlinear, non-convex, independent initial values. So those are the good points. Yeah, I think this is something which is very interesting. So for example, when we solve this problem, the earlier in the discretized graph cut setting, we always use a push relabel augment pass. We get their code and run the thing and show the result. Yeah, there's another weak point of a graph cut. So graph cut, you can only minimize very special minimization problems. With the segmentation, you can do it. But once, if you do registration, if you do deep blurring, then it doesn't work. Because a graph cut, the function you minimize must be, you must be able to sum it over a graph. And segmentation, you can do that. For this kind of problem, you can always, put it into a graph. But like a deep blurring and registration, and then you cannot put your energy into a graph. And then you cannot use a graph cut. But then the new approach here, you can still try to get around, you can still use it. And this is another thing compared with the graph cut. So for example, now we don't use a push relabel, and then we don't use augment pass. So what we do is essentially, so you try to use the max flow. Here we use a Lagrangian, but we even add penalty. So this is so-called augment Lagrangian. And for minimization people, this is well-known method. So one do this one. These constraints are convex constraints, so therefore it's very easy to deal with. So essentially, we put these flow constraints as a penalization of Lagrangian, and those will be the flow. These are the flow from the source to the every point. This is from flow from every point to the thing, and this is flow between the points, and this will be the cut. So there's very natural physical meaning for all the variables here. And those constraints, so this is normally you can put as edge detector. So here F1 is essentially U0 minus C1 square. Here is U0 minus C2 square. So this is for images segmentation, the very easy meaning. You put those ones, and then we just use alternating minimization methods. So fix a Lagrangian, and then minimize this one with those two fixed, and then we get this value, minimize this one with everything fixed, and then everything will minimize this one. And each minimization is very easy to solve. You have a convex constraints. This is a linear, this is a linear, this is a quadratic. So each problem is very easy to minimize with nearly no cost. And then here use a Lagrangian multiplier, you gradient descent. Because you see here so here we have a minus. If you have a plus, you use a greedy ascent. And so therefore, this is also very easy. So this is easy, this is easy, this is easy, this is also easy. And this is convex. And clearly see you get rid of the graph cut. We are solving a graph cut problem, but you don't use a traditional graph cut algorithm. And this is offer a lot of advantages. And this you can guarantee you are minimizing, maximizing a problem. And moreover, you see, graph cut, we have a huge memory problem. Here, you don't need to memorize a graph. So everything is like iterative methods. So you don't consume too much memory. And moreover, you see, everything can be done in GPU because it's a very simple operations. So everything can be done in GPU. Once you do it in GPU, so you get easy parallelization and you get acceleration quite a lot. So this is another point. Another point. Yeah, so I think we compare the, I think they use some kind of Bergen, split Bergen to solve a two-phase segmentation. So essentially this paper using the split Bergen. But one point I want to say is split Bergen is also Lagrangian. We didn't get time. We were planning to talk about this one in the second lecture, but we didn't get to talk about. But split Bergen, then there is also Lagrangian there. But that Lagrangian is due to the TV. But our Lagrangian even have a clear physical meaning. Our Lagrangian is a cut. So there is a very natural physical meaning here. Very natural physical. Here is a comparison. Here is a number of iteration. I think the red curve is our methods. And here is a split Bergen. Here I think is the. Here I can't remember. Here is an error. I think it's an error to the true solution. Yeah. So it goes much quicker than the split Bergen. Yeah. So therefore, I hope you get 1 point. So here you see you play around, turning the min cut max flow into the continuous setting, and you really see you get a lot of meaningful things. You get rid of some of the weak point of the graph cut things, and we have also compared with this method with the traditional graph cut. Even without GPU, it can be faster than the original graph cut algorithm. So I think I have passed this code to him yesterday. I just used 5 minutes to tell him how to use it. Maybe he can. Yeah, maybe you can show some demos of this one. Can you show it now, right? Yeah, maybe just show it now, and then we can take the break. So exactly, I passed that code to him yesterday because my computer, the MATLAB server, is in Bergen. I passed to him. He just used some minutes. He was able to do it. And the code he was trying to show, that was using exactly this two-phase continuous max flow approach using the Lagrangian approach. Yeah, so that's a code. I got. In the end, this code is public, so anyone can get it. I will tell you where is the web page. Yeah. So maybe you try which example? Maybe you try the cameraman first, and just to show how quick the yeah. This is the input image. We use k-mean to find the two constant value. You just segment it into two phases. Here is a regularization parameter. You regular the length. If you use a big regularization parameter, you see you only get to the min part. You reduce the regularization parameter. So here you reduce it a little bit, and then you get more detail. You reduce once more. Here you get more details. If you reduce even more, and then you get more and more oscillatory. So the alpha, which is regularization, controls the regularity. So here is too regular of the boundary, and here you get more detail. If you even reduce, you get. What's the size of this image? You can see how is the speed. If you have been working with other segmentation method, you don't approach this speed. So essentially, push the button. So here is 0.1 second to segment such an image. Even this is in MATLAB. If you do C or GPU, so that will be much faster. This is even 233 to 233. So if you use other methods, even I think it will become much slower. I mean, for example, if you segment this one, is a level set, how much time you may use?
Well, you're using next function actually.
Sorry?
You're using C code, right? Using next function.
Yeah, this may be, yeah, this is the Mac, right?
Actually, for me, I didn't use the next function, so it's not
All right. This is most probably, yeah, this is it's a C code we run in MATLAB. We run in MATLAB. Yeah. Can we now try with Barbara? You see such an image, you just 0.1 second. So that's, yeah, you try with a different regularization. And this is a much bigger image, and that is getting, you need to use about 8 seconds in MATLAB. Is it running? So the previous image is just 0.1 second, and this one you use a few seconds. When the alpha is bigger, it takes more CPU time. When the alpha is smaller and smaller, when regular, so this is a lot of regularization. You only get the principal part. So you only get you try the next regularization. All right. So the next you get more. You can slowly see even the eyes are coming out. The higher is coming out, and you use the next one. All right. And see here, if you use a smaller alpha, you get more and more. Yeah. So this is real time, a real image. How many seconds you use? Can you see the second? I think about 8 seconds. 8 seconds. This image is about 500. What's the size of this image? Did you show it? Yeah, 520, 500. This is a very large image. And try the Olympics. So that's he get the code, and he even just downloaded the Korean championship. So this was he downloaded. You see, this is a real image. You try to segment it into 2 phases. Yeah, this is a very big alpha. It takes more time to compute. You only segment using and then the next one is so here you get more is a little more details, more of the small scale. So here even smaller, and then here is more things comes out. More things come out, right? You see, this is real time, real data, and so also especially I'm trying to show there's a speed here. With a 500 something times 500 something, you can do in a few seconds, and that's really quite fast. I think you can make it even faster using GPU, or you use accelerated things.
Do you have any logic to choosing the alpha parameter, or you just fix?
The alpha, you have the regularization parameter. No, not here. So here, essentially, we just offer you one set of fast solver. If you really want to use it for real application, you need to expand the code quite a lot. So how do you choose alpha? How do you adaptively choose the constant value? Maybe now I can. Do you have any more to show? Or, that was enough. It was good. He was very clever. I just give the code to him, and he. We just used a few minutes together, so he was able to use it, and was really fast, So I think for real applications, you need to do something more. So here, this is also our paper, own paper, but I'm just trying to show you here that the industry are using quite a lot of those things. So you see, like here, we are essentially using this continuous cut, adding a little more constraints. So we try to add the constraint such that the region is a star-shaped. So star-shaped means always at the center, you go out, and then you only touch one point. You don't allow to touch 2 points. So this is star shape is a geometrical constraint. I think a lot of people are doing. Is here is a graph cut. Normally you see that there's no curve movement, but here we even try to use a graph cut for curve movement. Essentially, is a level set, you can move the curve. Here we just do the geodesic contour graph cut, which means you have a time step. Each time step I do a graph cut, and another time do another graph cut. You do many. So here you start with here, do graph cut, slowly do here. So because some people say graph cut, the level set, you move the curve. You see the curve is moving, you have a time evolution. Graph cut is just one shot, minimize, and then again the curve. But here we are just trying to mimic the level set one. So I put a time, and then each time step I do a graph cut, and then you do the curve evolution. You do the curve evolution. Here you see that normally graph cut we use for real application. So this is they call the graph cut. I use a mouse to click. This must be the foreground. This must be background. So it returns 3. Iter is 13. You already get the face. And this alter the behavior quite a lot if you put such a constraints. So here you use a mouse. I click. So here is the foreground. Here is the background. And here is what you get. Here what you get. And so therefore, if you put such a thing, that essentially means you see that multiplier. So here must be phase 1. Here must be phase 2. So there is you put more constraints into the minimization. That's very easily done. Here is if you use it for these kind of more difficult images, for these kind of difficult images, especially for ultrasound, very often the image is too bad. Only human beings knows where the surface should be. In this case, you see either you can use your hand to draw it. Another way you just put you see 2 curves. So I said those 2 curves must be the background, and this green curve must be a foreground. And then you use it, and then you convert it to something here. So you do such a kind of interactive, and similar here. If this is still not correct, you can use your mouse to click more and do a recut. And mostly that will improve the result. You recut again. Here is more test. So here you see that you draw a few curves, and that must be background, and this green curve must be foreground, and then you see this is what you get. So here is you get. So even if this one is not you are not satisfied, you can even maybe put a small thing here and then do a recut. You will get better and better. Here is also you put a curve here and put a curve here, and you see here you put this is the goat. Yeah. So you put the curve. You can really put the curve. If you don't put this curve, normally you don't exactly segment the head. You could segment the whole body. But if I put something up to here, and then you only get the head of the person out. If you don't do this one, everything, the closing and everything is getting out. So you see, you just make such a small constraints, and then, yeah?
You said that you're doing the practice and then the reverse evolution simultaneously, right?
Right.
So what if you just do the practice?
Yeah.
I think you will get the 2-phase segmentation, right?
That's right.
So which means that my question is that do you also get the same results, or the results, the final curve evolution better? I mean, if you do combine both, you get the better results than only using the practice.
What was your question? I didn't catch the question.
No, if you use the practice, you have 2-phase segmentation, right?
Yeah.
You would have a boundary.
Yeah.
The boundary and then in this paper you combine the curve evolution and the practice.
Yeah.
You also get the boundary.
That's right. Yeah. I think even
the curve is better than the
even for those results, you don't need the curve. So essentially, I just use a mouse to click. So the green is my inside, is a foreground, and the red is my background. Use a graph card, and then you will get such a thing. Even you don't need the curve or evolution. So that's just a constraint into your Marx floor.
So using your snapping, then you find the C1, C2.
So those, if you draw such a curve, the C1, C2 can also come in from those two curves. So you can update the C1, C2, or you can just even use those two curves to obtain the C1, C2. So C1, C2 is just intensity value, average intensity value of those curves. So even we don't need to do curve evolution. So we just draw those, you see, green, red, and then do one card, and then now you'll get to the final one. If you are not satisfied with that card, you put some more curves again, you do another card. Yeah. So here, yeah. So this one you see that, especially for difficult images, if you don't get something satisfied, so you put the red curve here to recard, and then it will include that part. They will include that part. But even this 2D is easy. 3D is here. How do you do 3D? So we also, so here is we did it in 3D. So here you try to find the tubular medical. Here is if you don't do any smoothing, here you do smoothing. Here is what we do, especially for this image. So you can see that you put for this image, you can see here we put a red point, here we put a blue point, green point, red point, green point, red point. So this confines, and then in the end, so you get the star-shaped fish. Also here you see that, so here you see here is a green, here is a red, you exactly get the face out. If you don't do such a kind of interaction, you may not exactly get the face. So here you see you put the red and green, and then you exactly get this one. Especially for this kind of application, you may need a lot more interaction. But the graph card is so quick, so therefore, so this is affordable. Yeah. So this is in practice. How do you use those algorithms? You do a lot of interaction. If the image is very difficult, you can use this one to slowly improve it. Even if you go to the Microsoft Azure, and there you see even you can they get the boundary. You can even use a mouse to drag the boundary by yourself and do a recard. That produces very, very good result. Only in a very small places you need to drag the curve. So this is how do you use it for practical applications. And very difficult images, if you do this one, because the speed is so quick, so you can really use it. Even this is quick. I think for 3D larger data, you still have a lot to improve. You still have a lot to improve to make it better. Yeah. So maybe, yeah, we can take a break now and then continue afterwards. Let's take a 15-minute break. We come back at 10 over 11. All right.